Today we shall see congruences for a prime modulus. We can think of congruences of the type fx congruent to 0 mod m for a general modulus m. But then if m is a product of prime powers, then first solving fx congruent to 0 p raised to r for you can combine so if I want to consider fx congruent to 0 mod m where m is product pi raised to ai I equal to 1 to r, then first one finds solutions of fx congruent to 0 mod pi raised to ai. If you know all these solutions for various pi dividing m, then you combine solutions by Chinese remainder theorem. Like, take a solution of this, let us say xi is the solution of fx congruent to 0 mod pi raised to ai. So x1, x2, xr, we get these are solutions for various pi raised to ai. Then you find out x congruent to xi mod pi raised to ai, a common solution to this system of congruences. A common solution to this system of congruences. So this is by Chinese remainder theorem. Then this common solution is automatically a solution of fx congruent to 0 mod m. Why? Because if x congruent to xi mod pi raised to ai, then f of x not congruent to 0 mod p square, then no t. There is no t between 0 and p minus 1, for which a plus tp is a solution mod p square. And suppose fa is congruent to 0 mod p square. That means a is a solution not only mod p but also mod p square, right? We are assuming a is a solution mod p. That means fa is congruent to 0 mod p. We are assuming further that fa is congruent to 0 mod p square also. If that happens, then see t equal to 0 is working. A plus 0 times p is the solution mod p square. But not only t equal to 0, every value of t will give rise to a solution mod p square. So then every t 0 less than equal to t less than equal to p minus 1 works. So this is a method of getting solutions mod p square from solutions mod p. And this method can be generalized to get solutions mod p cube from solutions mod p square in the same way that suppose a is the solution mod p square, then assume the same condition that derivative f dash a not congruent to 0 mod p. In that case a plus t p square I have to consider. For what values of t A plus T P square will be a solution mod P cube. Okay. A is the solution mod P square, I am assuming. For what values of T, A plus T P square will be a solution mod P cube. And the answer is similar. If derivative is not congruent to 0 mod P, T congruent to minus Fa upon P square here, F dash A bar mod P. This unique value of T will give rise to a solution mod P cube. Okay. Recall that in Newton-Raphson method of getting better and better solutions that you study in numerical analysis, the condition is derivative is non-zero. Xn plus 1 equal to Xn minus Fxn upon F dash Xn, where F dash Xn is assumed to be non-zero. Same condition is here. Then there is unique solution here mod P cube. If derivative is 0 mod P, then there are two cases. If Fa is not congruent to 0 mod P cube, then there is no T. If Fa is congruent to 0 mod P cube now, then every T will work and you get solutions mod P cube. Similarly, you can continue. So from solutions mod P, you get solutions mod P square. From that you get solutions mod P cube, P raised to 4 and so on. So this tells us that we should therefore look at solutions mod P. So we should study solutions of the congruence Fx congruent to 0 mod P, where P is a prime number. So since solutions of Fx congruent to 0 mod M for general modulus M can be systematically obtained from solutions of Fx congruent to 0 mod P for prime divisors P of M. We study this specific congruence. We study the congruence Fx congruent to 0 mod P, P prime. That's the reason why we concentrate on this study. Given the congruence Fx congruent to 0 mod P, does it have a solution? What kind of solutions it may have? And from that you can study the congruences for general moduli. So, is it that a congruence mod A prime always has a solution? That may not be the case, as you know. For example, you take x cube plus 2x plus 1 congruent to 0 mod 3. Does this congruence have a solution? If I take x equal to 0, answer is 1, which is not congruent to 0 mod 3. If I take x equal to 1, I get 1 plus 2 plus 1, that is not 0 mod 3. If I take x equal to minus 1, minus 2 plus 1, that is also 1 mod 3, not congruent to 0 mod 3. So this congruence has no solution. There are three possibilities. On the contrary, you can immediately think of congruences mod p such that each of these numbers 0 to p minus 1 has a solution. Okay, you have any question? Yeah, it has no solution. Just now we have checked that the three possibilities are there, 0, 1 and 2. These form a complete residue system. Okay, modulo 3. And none of them it is solution. So 0, 1 and 2 or minus 1. 2 is the same as minus 1 mod 3. So we have checked 1, minus 1 and 0, which forms a complete residue system mod 3, and this has no solution for each of them, and none of these is the solution of this. So no integer will be a solution of this. So this has no solution. If I take x cube minus x congruent to 0 mod 3, number of solutions of a congruence, polynomial congruence means what? You have to take some complete residue system, and how many elements from that complete residue system are solutions of such a congruence. The number of solutions means that. So here take any complete residue system like 0, 1 and 2, or you can take 0, 1 and minus 1. Each of them is a solution of this. So this is a congruence of degree 3, and all the numbers 0, 1, 2 are solutions. So it has 3 solutions. And so every integer is a solution. Of this congruence. 3 solutions means, number of solutions in any complete residue system. That's the meaning of number of solutions of a congruence. This, let us just recall that. Recall number of solutions of fx congruent to 0 mod any m is the number of xi belong to, let us say 0, 1, etc. m minus 1, or xi belonging to a complete residue system mod m, any complete residue system mod m, such that f of xi is congruent to 0 mod m, such that f of xi congruent to 0 mod m. So number of solutions. Here every integer solution doesn't mean that number of solutions of the congruence is infinite. We say that number of solutions is 3, because take any complete residue system that has 3 elements only here, because modulus is 3, and each of them is a solution. So this is actually coming from Fermat's little theorem, that access to P is always congruent to X mod P. P is 3 in this case. So another standard example coming from Fermat's little theorem is access to P minus X, this is our fx, congruent to 0 mod P, P prime, has how many solutions? P solutions. If your modulus is P, then you cannot expect more than P solutions. A complete residue system has only P elements. So degree is suppose very high. Your P is equal to 7, and you are considering a polynomial congruence of degree 100. Number of solutions is at most 7, that prime, because these are the only possibilities. So here, because number of solutions is possible solutions is limited, the things like what you have for complex numbers, number of solutions of fx equal to 0 is equal to the degree of this polynomial, and number of solutions are counted with multiplicity. That result cannot hold here. So upper limit is of course that p, and you can reduce the degree here and number of solutions. So let us look at this example. If I take x raised to, let us say 100 minus x raised to 98 plus x plus 1 congruent to 0 mod 3. What are solutions here? See that this thing is just x raised to 98 or 97, let us say, multiplied by x cube minus x plus x plus 1, this left hand side. And every value of x satisfies x cube minus x congruent to 0 mod 3. So this will be congruent to x plus 1 mod 3, since x cube congruent to x mod 3 for any x. Any integer x, we have this thing. This difference is 0 mod 3. So this is x plus 1. And then what is the solution of x plus 1 congruent to 0 mod 3? We can take x equal to 2. So this means that this is congruent to 0 mod 3. The above congruence holds if and only if x congruent to 2 mod 3. Okay, x plus 1 should be 0 mod 3. So x congruent to minus 1 mod 3, we can say it is 2 mod 3. So this congruence has only one solution. So this polynomial x cube minus x plays an important role in this. And this is an equation of very large degree, congruence equation of large degree. We have reduced that to the congruence equation x plus 1 congruent to 0 mod 3, which is an equation of small degree. Its degree is smaller than this number 3, the prime number 3. So by the same method, you can reduce the degree of the polynomial congruence and get an equivalent congruence of degree less than p. So that is the next result that we want to study. Theorem. If the degree of a polynomial congruence fx congruent to 0 mod p, here p is prime, is bigger equal p, then either every integer is a solution to the congruence, like x cube minus x congruent to 0 mod p has every integer as solution, or x raised to 100 minus x raised to 98 congruent to 0 mod p is 3, has every integer as solution. That can happen. Or there is a monic polynomial gx with integer coefficients and of degree less than p, degree less than p, such that the solutions of this polynomial gx congruent to 0 mod p are the same as solutions of the given congruence, such that the solutions of gx congruent to 0 mod p are the same as the solutions of fx congruent to 0 mod p. So either the original congruence has every integer as a solution, or you can get an equivalent congruence of smaller degree, moreover degree less than p, such that fx congruent to 0 mod p and jx congruent to 0 mod p have the same solutions, same integer solutions or same solutions mod p. Now to prove this, we divide fx by our polynomial x raised to p minus x, which you study in the Fermat's little theorem. Divide fx by x raised to p minus x, get a quotient and get a remainder. So proof: divide fx by x raised to p minus x. Let qx be the quotient and rx the remainder. So what we have got is fx equal to x raised to p minus x into qx plus rx. Here rx is identically 0, or degree of rx is less than the degree of x raised to p minus x, that is less than p. Now it may happen that all coefficients of Rx are divisible by P. That's a possibility. So if all coefficients of Rx are divisible by p. Now this includes the case Rx equal to 0. Rx may be 0. I am including that in this, that all coefficients of Rx are divisible by p. Each coefficient we can consider as 0. So divisible by p. Then what happens? Then note that by Fermat's little theorem, x raised to p minus x is congruent to 0 mod p. Okay. Then by Fermat's little theorem, x raised to p minus x congruent to 0 mod p for every integer x. And therefore, every integer will be a solution of fx congruent to 0 mod p. Is that clear? Look at this equation. Fx equal to x raised to p minus x into qx plus rx. We are assuming that all coefficients in rx are divisible by p. So whatever may be your x, that rx will be 0 mod p. Whereas for any x, integer x, x raised to p minus x will be congruent to 0 mod p. So this whole thing will be 0 mod p for any integer x. So fx congruent to 0 mod p for every integer x. Now suppose that one of the coefficients of Rx is not divisible by p. Next, suppose that from the equation fx equal to x raised to p minus x qx plus rx, we see that every solution of fx congruent to 0 mod p, that is already a solution of the first part, because x raised to p minus x is congruent to 0 mod p for every x. So that will be a solution of Rx congruent to 0 mod p also. We see that every solution of fx congruent to 0 mod p is a solution of Rx congruent to 0 mod p. And conversely, if you have a solution of Rx congruent to 0 mod p, then because of this part, Fermat's little theorem, that is a solution of fx congruent to 0 mod p. And conversely, so we have got a polynomial Rx of degree less than p. This is a non-zero polynomial because at least one of the coefficients of Rx is not divisible by P. Rx is a non-zero polynomial of degree less than P. That is one of the requirements. Only thing is Rx may not be monic. In fact, some leading coefficient of Rx may be divisible by P is possible. So what we do is, suppose some initial coefficients of Rx are divisible by P, you just get rid of them, and suppose M is the largest such that the coefficient of x raised to m in Rx is not divisible by P. So let m largest positive integer such that the coefficient of x raised to m in Rx is not divisible by P. Now you take a polynomial g1x by excluding the higher coefficients. Let g1x be the polynomial obtained from Rx by excluding terms of degree bigger than m. Okay, degree m plus 1, degree m plus 2, if at all they are there, just remove them. These terms have coefficients divisible by P, because m is largest such that the coefficient of x raised to m is not divisible by P. Then Rx congruent to 0 mod P and g1x congruent to 0 mod P have the same solutions. Because what we have removed is terms divisible by P. Okay, now only thing is, so see that g1x has the property that g1x congruent to 0 mod P and original congruence fx congruent to 0 mod P, they have the same solutions. Because fx congruent to 0 mod P has same solutions as Rx congruent to 0 mod P, and that has same solutions as g1x congruent to 0 mod P. Only thing is g1x may not be monic. So there may be some coefficient. So suppose b is the coefficient of x raised to m in g1x. Suppose b is the coefficient of x raised to m in g1x. Now if you multiply g1x by the inverse of b mod p, then you get a polynomial which has the same solutions as g1x. So let b bar be the inverse of b mod p. Consider So observe that B V bar is congruent to 1 mod P by the definition of inverse. So B V bar minus 1 is divisible by P. B V bar minus 1 is divisible by P. So consider B bar times G1x. Now here what is the leading coefficient? It is B bar. But we don't want B bar as the leading coefficient. So we subtract B bar minus 1 times x raised to m. B bar minus 1 times x raised to m. So you see that now B bar x raised to m is here. That gets cancelled with B bar x raised to m. So we get terms of degree smaller than x raised to m. Now minus plus x raised to m. So this becomes a polynomial starting with x raised to m. Monic polynomial. And that we call as g of x. Then this is a monic polynomial. Then gx is a monic polynomial what are the solutions of gx? This part B bar minus 1 is divisible by P. Okay? And therefore since B bar minus 1 is divisible by P, and B bar is not congruent to 0 mod P because B is not congruent to 0 mod P. So solutions of Gx and solutions of G1x, they are the same. Solutions in the sense of root. Gx congruent to 0 mod P and G1x congruent to 0 mod P have the same solutions. So in this case, we have obtained a polynomial Gx such that Gx is a monic polynomial. It is of degree m. M is less than the original degree of the polynomial. So here, that is m is less than p in fact. So here Gx is a monic polynomial of degree m less than p such that fx congruent to 0 mod p and gx congruent to 0 mod p have the same solutions. Okay, so this is the theorem that is that will be useful in the later part. The next theorem is about how many solutions are possible for a congruence of a given degree. So we know that if you have an equation fx equal to 0 with coefficients in a field or even an integral domain, then this equation has at most n solutions where n is the degree of fx. The same thing will be true here. Only thing is we have to consider the degree of the congruence, not the degree of the polynomial. Okay? So you are given fx congruent to 0 mod p, and if the degree of the congruence is m, then this congruence has m solutions at most. See that this is not true for composite numbers. Only for prime modulus we have a theorem of this type. As you already know, if you take a simple congruence like x square congruent minus 1 congruent to 0 mod 8, then 1 square is 1 mod 8, 3 square, 5 square, 7 square, they are all 1 mod 8. So this congruence has 4 solutions, which is more than the degree of the congruence. Degree is 2, and the congruence has 4 solutions. In any complete residual system, you will get 4 solutions for this congruence. So for composite modulus, the result is not true, but we shall be stating the result for prime modulus. So let fx congruent to 0 mod p be a polynomial congruence of degree n. Then the congruence has at most n solutions. Proof of this: now the congruence is of degree n. What does that mean? In this polynomial fx, we have the term a n x raised to n, and a n is not congruent to 0 mod p, and higher degree terms may be there, a n plus 1, a n plus 2, which are coefficients of x raised to n plus 1, x raised to n plus 2, and so on, but they will all be divisible by p. So the largest coefficient for the polynomial fx, which is largest means coefficient of the term like x raised to n, this coefficient. So the largest n such that the coefficient is not equal to 0 mod p, or not congruent to 0 mod p. That is n in this case. When you say the polynomial congruence is of degree n, then n is the largest such that the coefficient of x raised to n is not divisible by p. So in such a case, we can even think of the polynomial to be starting from x raised to n, because this congruence and the congruence after removing some higher degree terms, because their coefficients are all divisible by p, the number of solutions will not change, it will be the same. So we may assume that fx equal to a n x raised to n plus a n minus 1 x raised to n minus 1 plus etc. plus a naught ai belonging to z, and a n not congruent to 0 mod p. Okay. This is what, without loss of divisibility, we can assume that polynomial is of this form. Because although there may be some higher degree terms, because degree, the polynomial congruence is of degree n, so all coefficients of higher powers of x will be divisible by p, and there will not be any So the solutions are same. Solutions of fx congruent to 0 original congruence and removing those higher degree terms, same solutions are there. So it is sufficient to consider fx like this. Now we do this by induction. The proof is on n. So n equal to 0. So fx in that case is just a naught. Degree is 0. That means this is a naught and it is not congruent to 0 mod p by assumption. So the congruence has no solution. Okay? That means number of solutions is less than or equal to the degree of the congruence. N equal to 1, what happens in this case? Fx is equal to a1x plus a naught, where a1 not congruent to 0 mod p. And so what is the solution? a1x plus a naught congruent to 0 mod p, that's what we are having. A naught is not divisible, a1 is not divisible by p. Therefore, in this case, a1x plus a naught congruent to 0 mod p has a unique solution, since a1p equal to 1. So if a1 bar is the inverse of a1 mod p, then x congruent to minus a1 bar into a naught. That's the unique solution. So number of solutions is less than or equal to the degree of the congruence. Okay. So now assume that the result holds. For polynomial congruences of degree less than n. Now suppose if possible, fx congruent to 0 mod p has n plus 1 distinct solutions a1, a2, etc. up to an plus 1. Now consider another polynomial gx. Define gx equal to fx minus an into x minus a1. So let us not write these as a1, a2, an plus 1, but call them as b1, b2, bn plus 1. So an is the coefficient of x raised to n. So x minus b1, x minus b2, etc. x minus bn. Now gx has at least n solutions B1, B2, etc. Bn. It is possible that every coefficient of Gx is divisible by P. So case 1, is divisible by P. Now, if you put x equal to Bn plus 1. So G of Bn plus 1 will be 0 mod P because every coefficient of Gx is divisible by P. G of Bn plus 1 is congruent to 0 mod P. Therefore, f of Bn plus 1 minus An into Bn plus 1 minus B1, etc. Bn plus 1 minus Bn, this is also congruent to 0 mod P. Now what is f Bn plus 1? Bn plus 1 was a solution of fx congruent to 0 mod P. So this is 0 mod P, and therefore An into Bn plus 1 minus B1, etc. Bn plus 1 minus Bn congruent to 0 mod P. But B1, B2, Bn plus 1 are distinct, that is incongruent mod P. They are distinct mod P, that is incongruent mod P. So Bn plus 1 minus B1 is not congruent to 0 mod P, etc. Bn plus 1 minus Bn not congruent to 0 mod P, and An is already not congruent to 0 mod P. So this product is not congruent to 0 mod P, and we get a contradiction. Since An not congruent to 0 mod P and Bi, so Bn plus 1 minus Bi not congruent to 0 mod P, or 1 less than equal to I less than equal to n, we get a contradiction. Therefore, at least one of the coefficients of Gx is not divisible by P. But now Gx is fx minus An into x minus b1, etc., x minus bn. What is the leading term here? An x raised to n. What is the leading term here? An x raised to n. These get cancelled, and therefore Gx congruent to 0 mod P is a congruence of degree less than n. It has some degree because at least one of the coefficients of Gx is not congruent to 0 mod P. So it has some degree. What is the degree? Degree is less than n because the leading term gets cancelled. And therefore this congruence by induction assumption should have how many solutions? At most n minus 1. Therefore this congruence must have at most n minus 1 solutions. Okay, but already b1, b2, bn are solutions because f bi is 0 and here also that's a solution. But gbi equal to congruent to 0 mod p, 1 less than equal to I less than equal to n, and these are distinct mod p, and bi are incongruent mod p. So congruence is of degree less than n and the congruence has n solutions. This is a contradiction. To the induction assumption. And this proves the result. That is, fx congruent to 0 mod p, which is a congruence of degree n, must have at most n solutions. If you assume that there are n plus 1 solutions, we get a contradiction. Okay? That is, fx congruent to 0 mod p must have at most n solutions. This proves the theorem.